Hello, this is Tom Rummage of Micro Measurements. Today, Colin Mooney and Hugo, two applications engineers here at Micro Measurements, are going to demonstrate the bonding techniques for a 3-element rectangular rosette miniature. It's an S5198. It's a very, very small rectangular rosette designed specifically for circuit board testing. We're also going to have a G1350 bonded to this circuit board. And then we will use a drop test fixture, and we're going to drop 3 separate loads, a 80 gram, 133 gram, and a 225 gram load in our drop tube. And we're going to be testing to the JDEC 9704 spec from 2005 and 2012. They're 2 separate specs with 2 separate sets of calculations. During that testing, we're going to see if it passes or fails the strain rate test. There's a certain set of criteria that if you're below that certain set of criteria, then it passes. If you exceed that, it doesn't pass. And it's our anticipated understanding that the steel ball, the 225 gram weight, will cause this circuit board to fail. And that's based on the JDEC spec. First step, we'll use the GC6, the isopropyl alcohol. And the isopropyl alcohol is used as a degreaser because it's fairly benign. It doesn't have an aggressive nature like our CSM3. Some circuit boards can be degraded if you use too aggressive a solvent. And he's going to take the location where he's going to put the gauge, and he's going to lightly degrease it right around the corner of the ball grid array. And then he's going to throw away that piece of that piece of gauze sponge. He's going to locate the 400 grit silicon carbide paper, or SCP3, and he's going to lightly dry abrade the location. You don't want to take away too much material because this is a fairly thin section, and also it doesn't really require a lot of abrasion. Once he's happy with his dry abrade, he's now going to take the conditioner A, the MCA-1, and a cotton tip applicator, and he's going to scrub the organic materials away, the dust and debris that he's just created when he did the dry abrade, and also any organic contaminants that might be present. And this is a mild phosphoric acid solution. Once he's completed that scrubbing with the conditioner A, he'll take a dry gauze sponge and with a single wiping motion absorb the excess material. The next step is to use the Neutralizer 5A, the blue tip bottle, and this will get the pH back to nominally neutral or slightly basic because the cyanoacrylate adhesive system we're going to be using is pH sensitive. So he's going to use the Neutralizer 5A and again scrubbing the surface of the part. What this is doing is it's the stop bath for the conditioner, if you will, and setting the pH to be the proper level, either neutral or slightly basic. He'll take another dry gauze sponge, fold it into quarters, and absorb the material. A secondary step of drying, because the circuit boards are somewhat hygroscopic, he's going to take a warm air blower and he's going to warm the surface, driving any residual moisture from the Neutralizer 5A off the board. You don't have to do it for very long, and it doesn't have to be terribly hot. We just want to make sure and drive the moisture off the surface because the M-Bond 200 is negatively affected by too much moisture. He's now going to clean his glass plate and lay out the S5198 gauge there. He'll use the Neutralizer 5A, a couple of drops. With a dry gauze sponge, he'll scrub that surface of the glass, making sure there's no contamination there. Now, because of the fragile nature of this gauge and the lead wires that are attached, he must be very careful when removing the gauge from the acetate folder. Just slides it out. He's now going to lay it out, unfoil a little bit of the wire so it's convenient to work with, and he's going to lay it out on his glass plate, and using the PCT 3M tape, he's going to apply the handling tape so that he can align it on the specimen. You notice he threw away about 2 inches of the tape. That might be contaminated. With fresh tape, he's going to place the tape across the gauge. Needs to get it down on the surface. He's putting the tape transverse to the long axis of the lead wire because that's more convenient and less susceptible to damage when you're removing the tape. Having successfully adhered the tape to the gauge, he's at a shallow angle. He's going to lift the tape up until he removes the gauge from the glass plate. He's now going to position the circuit board, the properly surface prepared circuit board, and position the gauge in the location of interest, normally near the corner of a ball grid array or the corner of a component of interest. He's now going to expose the bonding surface of the strain gauge by lifting the tape again at a shallow angle until he gets beyond the gauge. And he's going to tape it back on itself. We now need to apply the catalyst C. You're going to have to tape that down. It's just going to jump up. Now the catalyst C on the inside of the neck of the bottle, he's going to hit it 8 to 10 times, removing almost all the material from the brush. You don't need a whole lot. And with a squeegee motion, he's going to wet the backing of the gauge. The catalyst C is actually a controlling agent necessary to make sure that the adhesive system cures uniformly. And he's going to wait one full 60-second minute for all the isopropyl alcohol, the carrier of the catalyst C, to evaporate. If he didn't wait for a minute, he might have the alcohol would be a contaminant. We now have our 1 minute of air dry time necessary to get rid of the isopropyl alcohol. He's now going to use the M-Bond 200, the cyanoacrylate adhesive system, and he's going to place a single drop at the cusp of the tape and the circuit board. This allows the adhesive, as it touches the air, it begins to catalyze, and you want to have fresh adhesive underneath the gauge. So a single drop. He's going to fold it over. With a gauze sponge, he's going to squeegee through, and he's going to use 1 minute of thumb pressure. Well, in fact, he's going to use he's going to use thumb pressure. He's trying to mess with me here. And 1 minute of thumb pressure, the heat from your hand and the pressure from your hand are what are going to catalyze and or cure the M-Bond 200. And a minimum of 1 60-second minute. It takes a while. We've now completed our 1 minute of thumb pressure and then 2 minutes under the tape, the standard cure process for our M-Bond 200. Colin is now going to very carefully peeling the tape 180 degrees back on itself, putting the adhesive into shear as opposed to peel. He's going to remove that gauge handling tape. Appears he was successful. And before we do anything else, we're going to tape down those lead wires. This is a very fragile installation until the lead wire is strain relieved and stabilized. And because of the short-term nature of the testing of the impact testing of a circuit board, we're going to dispense with an environmental protection. We're in an air-conditioned and heated room at 50% relative humidity, so there's no reason for us to put down an environmental protection. Next step, test the beam or test the board. All right, now we're into the testing phase of this particular circuit board application. And I wanted to show you we bonded the G1350 and the S5198 on the back side on opposite corners of a ball grid array. We're going to mount this in our bed of nails test fixture. We'll close the lid, and this is simulating the probe sets that come up and measure the strains, and we're going to zero this out because we're not interested in that in this particular drop test. I have this tube which will keep my, my drop on target. I have an 80 gram, a 133 gram, and a 250 gram load that we're going to be applying to this. And we're going to be dropping this down in this tube to look at the strain rate and the pass-fail criteria based on the JDEC standards. We've now set up the System 9000 with StrainSmart software, the newest version of it that has all the JDEC standards calculations involved for strain rate and failure criteria and that sort of thing. We're going to zero it and then calibrate it, taking any offsets that are out of the picture, taking any lead wire desensitization out, and then using a manual command I'm going to drop this and we're going to make a scan session with the lightest weight, the 80 gram weight. So go ahead and start the manual record. Ready? Go. Our next drop test will be a 133 gram drop, and we anticipate both of these lighter drops not to fail the JDEC spec and the last one to fail. So ready? Start. This will be our final shot. We're going to be using a 255 gram steel ball, which we anticipate will cause this particular circuit board and or the results to cause a failure based on JDEC spec, the JDEC specs. So ready?
Mad scientist.
Our final drop test is we're going to be using a 387 gram ball, and in this particular case we're almost certain that it's going to give us a fail criteria for the JDEC specs in strain rate. So Matt, you're ready? Or Colin, you ready? Now here's our data from that last drop test, the big ball, the one that was 350 or 380 some odd grams. This is the actual strain data. You can see a peak somewhere around 1100, and this is the strain rate data. This is the JDEC standard has a specific calculation that challenges the strain or calculates the strain rate and gives you a failure criteria. And in fact, this particular ball drop in the JDEC specifications, it failed. Based on the JDEC standard, this is the failure criteria right here. This is the threshold of failure. And you'll notice that a large number of the points are down here below it, but there's a significant number that are above it now. And in this particular case, because those are above the line, that threshold of strain rate, it has in fact failed. And within StrainSmart, we can look at the report, and it also down here has taken that failure criteria into consideration, and it says, you got too much strain. You're going to fail that ball grid array, or at least that's what JDEC says.